Hello students, welcome back. The final lesson video on preliminaries will cover modular equivalence. This one I regard as a semi-optional video because we are going to talk about something that's showing right away. Right away I mean by as early as week 2, possibly even week 1, depending upon how quickly I move. Okay, let's begin. Here's a reminder on Cartesian product. Yes, and also a reminder on making those as precise as possible. Okay, everything is well defined. Everything is rock solid, and from there we can start and define a relation. Any non-empty subset of a Cartesian product is defined as a relation, and here are some examples of relation. A function, an equivalence relation, and an order relation. Remember all those? Here, the order relation is not that important for us here in algebra. It's important in analysis, yes, but not for algebra, so let's not worry about it. A function, we already went through this and it's a bit too elementary. It's the equivalence relation we are working on. And here's a bit further reminder on it. We have to have reflexivity, symmetry, and transitivity. By the way, if you want to have a little bit more precise expression based upon the pair expression, Cartesian product, set theory, and you can rewrite everything like this if you want to. I don't, so let's just skip those. And from there we can define equivalent classes. Set of all elements that are related to the starting element, which we call a representative. And the equivalence classes have these interesting properties. They are either identical or disjoint, either black or white, no gray. And then because of this, there are so many duplicates, so trim them all out and rename, rearrange as x1, x2, x3, and so on, and then take the union of different equivalent classes. Then by the second property, they are not just different, but they are all disjoint, so that we get a partition, which we call an equivalent partition. And the set of all equivalent classes is called a quotient set, and the cardinality of the quotient set can be significantly less than that of the that of the original set, because each equivalence class can be humongous, but the number of equivalent classes may not be that large, because there are so many overlaps, so many duplicates. Remember that, and let's go to a concrete example of modular equivalence. We start from the set of all integers, which corresponds to capital X, and we take any positive integer m, and we define a relation, congruence modulo m, or equivalence modulo m, like this. A and b are congruent modulo m if and only if m divides a minus b, or equivalently speaking, a minus b is divisible by m, so that we have to have a quotient q, which is an integer. This final expression is the most useful in most of the proof problems. And there's an existential quantifier here, which means whenever you use this, you have to take different q values. So use q1, q2, q3, q4, things like those, or q, r, s, t, and so on and so forth. Do not use same q twice. If you have universal quantifier, then you can use the same epsilon over and over, but for existential, no, you can't. Okay, all right, here's the first exercise. Prove that this is an equivalent relation. In other words, we have to prove that this is reflexive, symmetric, and transitive. Okay, here's the proof. Reflexive. You have to prove that A is related to A, so according to this, A minus A must be divisible by M. See? A minus A must be divisible by M. Some integer times M. What is this integer? Of course, that's 0. That proves the reflexivity. Now the symmetry, how about that? A divides B, which means A minus B is divisible by M, then B is equivalent to A, so B minus A is divisible by M. That's what you have to establish. A minus B is divisible by M, then B minus A is divisible by M. So if you have this integer, which integer will this be? That's the question. What do you have? Negative of that integer, of course. Starting with Q, then we get negative Q. How about the transitivity? That may be a bit wordy, so please start the playback and try. What do you get? Remember, you have this and that, so this one will give you a Q value, and that'll give you a Q value, and you have to use different characters here. You see, whenever you use existential quantifier, use different Q values. So A minus B is something times M, B minus C is something times M. Here, make sure you have two different characters here. Well, in my notebook, I use Q1 and Q2. So Q1M, Q2M, and then A minus C. Well, how do you prove it? All you have to do is just add them up. A minus B plus B minus C will turn out to be this. Consequently, we get Q1 plus Q2M. Make sense? Okay, that was an exercise. Now let's go to a little bit higher level exercise, just a little bit. Addition is well defined and multiplication is well defined. What do you mean by that? That means even if we take different representatives, the end result is the same. So same equivalent class can have different representative A1 and A2. And then if you induce the addition in the quotient set as addition of those representatives, then different representatives may give you different results versus all the same. That's a question. Turns out they're all the same, so addition is well defined. Same for multiplication. How to prove that? What do you mean by two equivalent classes are identical? That means those are related. Remember? So representatives are related. That's what you have to prove. A1 plus B1 and A2 plus B2 must be related. See? A1 and A2 define the same equivalent class, so A1 and A2 must be related, which means they're congruent modulo M, or like this. And then same goes to B1, B2. Again, here I used different character Q and S because we have existential quantifier. And then we have to prove something times M. How do you do that? Once you set up as much as this, it's not too hard. All we have to do is just add them up and rearrange. Do you see A1 minus A2, B1 minus B2? Indeed, that's what you're going to get. A1 minus A2 is QM, B1 minus B2, SM, and then if you just add them up and rearrange, you get QM plus SM, so that you get Q plus S times M. The setup here, that may be a bit of a challenge, but algebraic manipulation was not. How about the next problem? How do you set up? These two are related, and these two are related, then these two must be related. Happy with this setup? A1 and A2 are related. So we have Q times M. B1 and B2 are related, so we have S times M. And now the products are related, something times M. The problem is, how do you algebraically deduce this? Previously it wasn't that bad. I mean, same setup basically, except for algebraic operation. But the proof wasn't too bad. All I had to do was simply adding them up. What about this time? Any idea? You cannot just add them up or multiply. Any idea? The key is to subtract and add the same thing. Just minus A2B1 plus A2B1. Because I subtracted and then added the same thing, no difference there. Net change is 0. But this allows me to take this factor B out and that and factor A out. Let's go. First two terms, next two terms, and then first two I can factor B1 out. Second, I can factor A2 out. And then we have Q, S, okay. Factor M out and we get the answer. You see, this technique, subtracting and adding the same thing by cross-multiplying, this technique is very, very common in analysis. When you have to prove something about continuity or prove something about limits or even derivatives, this thing shows up a lot. For algebra, it's a bit less frequent, but it did appear here. So the conclusion. Addition is well defined. Multiplication is well defined. So the quotient set has well-defined addition and well-defined multiplication. Finally, what is this quotient set equipped with all addition and multiplication and everything? Turns out it's the same as a residue class, 0 to m minus 1. Do you remember the quotient set can have significantly smaller cardinality compared to the original? Well, here we go. Original has infinite set. This one has cardinality of just m. Same as this m. How do you prove that? Well, just division algorithm and that's it. Any arbitrary n, apply the division algorithm, then we have n equals to qm plus r, where r is a remainder, so it should be between 0 and an m, you see? R is a remainder. And then if you flip this r to the other side, and then n minus r is qm, so that's divisible by m, so n and r are equivalent. So no matter what n I select, what integer I select, it's got to be equivalent to one of these. And the reason is division algorithm. And here's the conclusion. No matter what I select, from the quotient set, no matter what equivalent class I select, it's the same as one of those remainder class, one of the residue class. So what did he establish? In this residue class, addition and multiplication work out just fine, and we just use induced addition and multiplication from the original integer set.